Hey, welcome back. And so this one I'm actually throwing into the middle of a whole bunch of pre-recordings I already did. When I was going back through the solving differential equations using the Laplace transform, I realized there was one example I hadn't really been thinking of, and it was the last one in the section. I thought it was really clever. So for the most part, when we're working with the Laplace transform, we're kind of stuck with only being able to solve differential equations with constant coefficients, linear differential equations with constant coefficients. But there are a few cases where we can actually take advantage of having non-constant coefficients. And this comes into the last example of the section, and there we have t times y prime. And what's really cool there is that t times y prime, we know when we take a Laplace transform that ends up giving us the Laplace transform of the derivative of the original Laplace transform. It gives us the derivative of y's Laplace transform. And so then what you end up doing is you trade a one hard differential equation for an easy differential equation. But of course, you're going to solve it. It has to be an initial value problem, otherwise you're going to get a general solution. And so one of the big features in there, one of the things that we end up taking is not that we have an initial value problem like what we usually do, but that we actually know that the Laplace transform should go to 0. And I'll explain that in the video. And so then we basically use this limiting relation in order to eliminate one of the constants that come out from integration. And what's interesting is that in that case, it actually works a lot like what you see in quantum mechanics, where they have a lot of these differential equations that are second order partial differential equations or whatever, and they need to get a hold of a couple of coefficients that come out of their bounds. They end up having sort of these second order systems. And basically they know that as you go to positive and negative infinity, you're going to need your states or your solutions to the differential equation, the PDE rather, should be going to 0. And so the same sort of reasoning is being used here, where we know the Laplace transform should go to 0. And so even though it satisfies the differential equation, we know that the coefficients that would come out for the general solution, they have to vanish because otherwise we wouldn't have the Laplace transform going to 0. So yeah, I think that's really interesting, and so we'll take a look at that. In any case, yeah, I hope everybody's doing well, and let's jump into it.
All right, so welcome back. So we're continuing doing some examples from section 7.5 on solving initial value problems with Laplace transform. All right, and so far we did the first two examples. The third example is where we're shifted and we're not starting at 0, rather we're starting at pi. I'm going to leave that to you to go and look over if you want. The methods don't really change that much. There is a little bit of shifting that happens, which ends up coming out as an exponential popping out. But I think what's really interesting is if we take a look at, say, example 4. So here they give us y double prime plus 2 times ty prime plus or minus 4y. And this is equal to 1. And they tell us that we have y of 0 is equal to y prime of 0, and these are both equal to 0, so that we don't have to worry about the initial conditions popping up in the Laplace transform anymore. But what's interesting here is that we end up differing from the other ones where we have constant coefficients. Now we actually have a coefficient that depends on t. So this is going to change things up a little bit, and so we have to sit down and recall a couple things. So remember, we already have the second derivative, the Laplace transform of the second derivative of y is going to be coming out as s squared times y of s. This is minus s at y of 0 minus y prime of 0. But again, we know that y of 0 and y prime of 0 are both 0 in this case, so we don't have to worry about those. We also have the Laplace transform of y prime is equal to s times y of s minus y of 0, but again, that is 0, so we don't have to worry about it. But we don't actually just have Laplace transform of y prime. In fact, what we have is we have the Laplace transform of ty prime. And so remember back when we were talking about special properties, we said if we take a Laplace transform of t times some function f, then this comes out as the derivative with respect to s of the Laplace transform of f. So, with a minus sign. So, the Laplace transform here then is t y prime. This is going to be the derivative with respect to s of the Laplace transform of y prime, which is s times y of s. And what that's going to give us is it gives us y of s plus, minus this. So we get minus y of s, and then we have minus s times y prime of s. All right, so now let's go ahead and put all these together. So we know the Laplace transform of this guy, and this guy, and we can go ahead and write it up. So we have s squared times y of s plus 2, let's say now minus 2 times y of s plus s y prime of s. Here I'm already factored out the minus sign and I put it here. Okay, and now I have minus 4 times big Y of s is equal to the Laplace transform of 1, and we know that is 1 over s. Okay, so now let's go ahead and collect all of our y terms, and so now we have, say, s squared minus 2, then we have minus 4, so that's going to be minus 6 times capital Y of s. Then we have minus 2s times y prime of s is equal to 1 over s. Okay. Now, what this actually, if we look at this, this is a differential equation in capital Y with dependent capital Y and independent variable little s, and it's actually linear in Y. So what I'm going to do is I'm going to go ahead and isolate this out. So I'm going to divide by negative 2s. And so what it's going to give me is going to give me this leading term, y prime of s. Then I'm going to have minus s squared minus 6 over minus 2s. Or, well, we're already incorporating the minus signs. So over 2s is equal to 1 over 2s squared. And this is times y. Okay, so now what do we have? We now have a differential equation that is linear. And not only is it linear, it is in terms of our Laplace transform, which is really interesting. So what do I need to do next? Now I need to go ahead and I need to write, I need to come up with an integrating factor, mu of s. And so my integrating factor is going to be the same as what usually it would be, e to the integral of p of s ds. And so this is going to be e to the integral of s squared minus 6 over 2s and a minus sign. So I'm going to go ahead and write this out. So it's going to be s over 2, and then it's going to be minus, minus 6, so 3 over s. Right, ds, and now we can go ahead and integrate that. That's going to be e to the minus, we're going to have s squared over 2, so it's s squared over 4, minus 3 ln of s. Right, and that's what we have as our integrating factor. Okay, cool. So, let's go ahead and multiply by our integrating factor all the way through. So, what do we get? So we get e to the minus s squared over 4 plus 3 ln of s, this times y prime of s. And now, you know what, I don't really feel like writing it a million times. Okay, so we multiply it there too. And so we have minus this, we have s squared minus 6 over 2s times y of s, 1 over 2s squared, and times e to the minus s squared over 4 minus 3 ln of s. There, so that's what we have. Okay, so left-hand side just becomes e to the minus s squared over 4 plus 3 ln of s. And this times y of s. And now all of this is the derivative with respect to s. It's basically inverting the product rule. And now we have this other term here that we need to integrate. Okay, so I'm going to take all of this and we're going to go to the next page. If I can just lasso it. Boop, 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 boop. And there we go. All right, so copy that, go to the next page. There we go. Okay, so what do we got? So integrating the left-hand side is just going to use the fundamental theorem of calculus. So this just leaves us with e to the minus s squared over 4. All right, so I'm just going to go ahead and break down, and this is actually going to be s cubed here out of this term, right? Oh, and I think I made a mistake. This should flip sign here. Because I think over here, yeah, we're distributing this minus sign over, and so that plus, this should be plus. Okay, so that makes this guy plus, and there we go. All right, so right, so then basically the 3 moves into the ln of s, so this whole thing becomes ln of s cubed, and so then not e to the ln of s cubed is just s cubed. Right, okay, so that's what we got on the left-hand side. On the right-hand side, we are integrating with respect to s, but let's go ahead and convert some of this out. So we have 1 over 2s squared, and now we have e to the minus s squared over 4. Now again, I'm splitting this off as s cubed, and all this is integral ds. So s cubed cancels out the s squared, but leaving a 1 power on the top, and so now we have this guy is equal to s times e to the minus s squared over 4, and all of this divided by 2 ds. Okay, great. So this actually, we can use U-Substitution. So we say u is equal to minus s squared over 4. When was the last time we did that in differential equations, huh? And so then we get du is equal to minus 2s ds over 4. And so then that means that ds is equal to du times 4, well, really just times 2, divided by s and a minus sign. And so what happens when we plug all that back in? Well, we get 1/2 out in the front. Integral of, looks like ds is turning into minus 2 over s. We have du. Let's see. So this is coming from the substitution for ds. And then we still have s in here, e to the minus, well, this was made to be u. And this is being done du. And these s's cancel, just like we'd want. In fact, the 2 cancels here, right? And that's good too. So now we're just left with minus integral of e to the minus, or actually it's plus u, so e to the plus u du. And so then that integral is just minus e to the u plus c. And all right, now let's change this back. So we have e to the minus s squared over 4, and plus c. Okay. All right, so now what do we got? So on the left-hand side, again, and here I forgot to include y of s because we were just inverting this guy. So we'll put that in there. And now looking through, I'm going to have y of s on the left-hand side. We're going to multiply times e to the s squared over 4 to cancel that. And then we're left with the s cubed. All right, so what do we have? So if I multiply both sides by that, I get, I'll just leave the s cubed here for a minute. is equal to, say, minus 1 plus c times e to the s squared over 4. And now if I divide by s squared, I get y of s is equal to minus 1 over s cubed plus c over s cubed times e to the s squared over 4. Let's put that more in the exponent. Okay, so we have something for our Laplace transform of y. We can definitely invert this guy. That's basically going to be, say, t squared. Minus t squared maybe divided by 2, I think, just because we're missing the 2 factorial in the numerator. But what's left here is this term. We don't have this in our table, this e to the s squared, which is really, really big. And then we have to figure out how to figure out what this constant c is. Well, there's something that we know, and it's basically this. If a function, say, if y is of exponential type, say alpha, for some alpha, then basically we know that y of s has to go to 0. And we can talk about why this is true in a minute, but we're going to take this as true. Well, so if y of s is going to 0, well, that's going to 0, and that's fine. That's good. But over here, this is definitely not going to 0. This is s cubed, but s cubed is always outcompeted by an exponential, and this is not just an exponential, but it's an exponential with a s squared on the inside. So this is definitely going to infinity. So this is to infinity. So we don't like that. And the only way to get rid of it is that basically c has to be equal to 0. So that tells us, ultimately, that y of s must be equal to minus 1 over s cubed. And if I write it like this, where I put, say, 2 factorial up here, s cubed, and then divide by 2 factorial to compensate, then basically what that tells me is that we have minus 1/2 the Laplace transform of t squared, right? And so that tells me that y of t is equal to just t squared. That might be a lot of work to get at just t squared. That feels a little unsatisfying, to be honest. But there you go. And not quite t squared, right? Times negative 1/2. So maybe I can spread that box out a little bit more. All right, please excuse me as I do this tedious box deletion. No box. There we go. All right, now we got this. There we go. Okay, so good. So we have negative 1/2 t squared. And yeah, that's the solution to that. So what did we do? So we got kind of lost in the woods here for a little bit. So basically what I saw is that I had a differential equation that didn't have constant coefficients on it. It's still linear in y. And so I said, okay, well, if I take a look at the Laplace transform of y prime, I can get the Laplace transform of ty prime through this whole differentiation thing. So I went ahead and did this whole differentiation thing, and using product rule is what it gave me. Thankfully, all of our initial conditions are 0, so that just disappeared. And then after that, we just solved for y as best we could. So we isolated all the terms that had y, and we saw oh no, we had a term with y prime. That's not good. So then we said, okay, well, we're left here. What do I do? Well, then I said, don't panic. This is a differential equation. It's a linear differential equation because it's linear in y. So all I need to do is, stick to my guns and come up with an integrating factor. And that actually ended up being not too bad. Once we multiplied that through, we got this term here, and then we continued to work over here, and then we integrated just using U-Substitution. I might have took a little too long to do that U-Substitution, and ultimately it gave us this here. We ended up having some constant though, and we didn't know what to do with it. And so I used this notion here that we'll go over more in a second, is that if y is of exponential type alpha, for some alpha, then y of s has to go to 0. So that told us, well, this is definitely not going to 0 if c is not 0. So then that tells us that c must have been 0. So then y of s was known simply as negative 1 over s cubed, and so then we can just figure out what the Laplace transform what function Laplace transforms to 1 over s cubed, and that's that. And so that told us that y is equal to t squared. Not bad at all. Okay, so if we go ahead and take a look at the book, they talk about this little theorem. They don't actually call it a theorem, but they say if ft is piecewise continuous on 0 to infinity and of exponential order, then the Laplace transform goes to 0 as s goes to infinity. They tell you that an outline of the proof of this is given in section 7.3 on page 366 in here. And if you go look at that page, it is problem number 26. They don't really give us that much. They tell us that f of t must be piecewise continuous and of exponential order. Show that you can extend this exponential order thing to work all the way up to 0. And then they say by using a definition of the transform and using part A, prove that it goes to 0. That's really not a lot to go on. And so maybe the problem's a lot easier than I think, but I'll give you my proof, which really doesn't require part A. So yeah, let's take a look. So let's take a look and just do the proof. So proof here. Okay, so what do we got? We know that f of t is of exponential type, right? That's what we're saying. So f of t is less than or equal to m times e to the alpha t for large enough t. And the idea that you can extend this to 0, that's not actually all that bad. If it's piecewise continuous, then on the interval from 0 to t itself, f of t has some bound, and then you just need to make m big enough to cover that bound. So that's not actually too remarkable. So we can sort of leave that. But the thing that what we're going to do is we're going to use the fact that it's of exponential order, and that tells us that the Laplace transform f of s, it exists for all s bigger than alpha. And I'm going to pick some particular s naught to be bigger than alpha. All right, so now instead what I'm going to be looking at, I want to consider this limit. So the limit as s goes to infinity of f of s naught plus s. Right, and I want to show that this goes to 0. So we want to show this limit is 0. Okay, so how are we going to do that? So it may be a little bit tricky. I don't know. It depends on how you take it. I had to give it a little bit of thought. But basically, if we take a look at the integral, so we know that big F of s naught plus s, this is equal to the integral from 0 to infinity of f of t e to the minus s naught plus s t dt, and so then you can even break it up like this: f of t times e to the minus s naught t, and we're going to separate this off, times e to the minus st. So yeah, so that's what we got. The reason why I did this is because if we try to get this out of the integral, I can rest assured that the integral still converges because of this guy. We know s naught is big enough that this would converge. But we'll get to that in due course. But in any case, let's go ahead and pretend m is constant and f is constant. And what we can do actually is we can just go ahead and use our triangle inequality and move the absolute values on the inside here. And then since exponentials are positive, the only thing that needs to be hit is f of t, and we can use the fact that it's of exponential order to replace it like this. So we get m times integral from 0 to infinity of e to the alpha t times e to the minus s naught t times e to the minus st dt. All right, and just to make life a little bit easier, I'm just going to combine s naught and alpha. here like this. So we only have to consider two functions, this guy and this guy. Okay, and that's an m there. I don't know. Maybe I need to work on my handwriting. So if you look at it, this is just a decaying exponential when you put everything together. So it's going to be 1 here, and then otherwise it's going to be concave up and going out like that. Being concave up means it's what we call a convex function. So if I take 2 points, then this triangle, this line will always stay over top of them, and we'll need to use that in a minute. So what do we have? So what I'm going to do here is I'm actually going to split this integral into 2 pieces. So I'm going to split it at 1 over square root of s. And the reason why I'm doing that is because I'm going to have 2 pieces. One where I'm going to get a bound on the integral basically by picking s here, and then I'm going to get a bound on this part of the integral that's going to depend on this height, and that needs to go to 0. And then the rest I need to make sure that this area goes to 0. In particular, when I do that whole convexity thing. So I'm going to split the integral in these 2 pieces, and we'll see how it works out. So let's go to the next page. So basically what we have is we have an absolute value of f of s plus s naught plus s. Let's try to keep things a little bit nice. So s naught plus s is less than or equal to m times the integral from 0 to infinity of e to the minus s naught minus alpha t times e to the minus st dt. Okay. So like I said, I'm splitting this into 2 pieces. So I have m times the integral from 0 to 1 over square root of s times e to the minus s naught minus alpha t e to the minus st dt. And then we have the other part, the integral from 1 over square root of s to infinity of e to the minus s naught minus alpha t times e to the minus st dt. Okay. All right. So let's see. We're going to look for ways to make things bigger, but allow them small enough that everything converges. So for instance, this piece here corresponded to that first bit of our integral. So it's something that's sort of going down like this, and we're stopping at 1 over square root of s. So if I pick these 2 endpoints here and here, then this piece is going to be bigger than the actual term here. So I can make another inequality. So I have m times, now if we want to find the area of a trapezoid, we take this height, we take this height, we take their average, and then we multiply it by the width, and that's what it gives you. So at t equals 0, we just get 1, and at t is 1 over square root of s, we get e to the minus s naught minus alpha 1 over square root of s times e to the minus square root of s, because t is 1 over square root of s, and so that cancels one of those. Right, and so we have this. Actually, I just want to scoot it down just a little bit. And then this is multiplied by 1 over square root of s. Okay, now for this term, what I'm going to do is I'm going to pick something that's bigger than all these. So e to the minus st, as t goes to infinity, is strictly decreasing. So if I just pick whatever the value is here, I can make this integral bigger just by replacing this guy with e to the minus square root of s, or whatever t was at the end point. So we get e to the minus square root of s. I'm going to pull that out. And then I'm left with this integral, which is actually bigger. So 1 over square root of s to infinity of e to the minus s naught minus alpha times t dt. Okay, and we can even make this a little bit bigger if I replace 1 over square root of s with just 0. Right, so instead of doing the integral from here to here, I say, all right, we'll take it all the way back. Right, and so that's actually getting bigger. So what do we get? We can work this out if we want, but it's ultimately some constant that doesn't depend on s. It only depends on s naught and alpha, and so this is just some constant here. And so let's go ahead and write things out. So we have less than or equal to m times 1 over square root of s times 1 plus e to the minus s naught minus alpha in tiny writing over square root of s times e to the minus square root of s plus e to the minus square root of s times some constant. All right, now let's see what happens as s goes to infinity. So as s goes to infinity, we have this piece goes to 0. And that's because e to the minus s as s goes to infinity, e to the minus square root of s as s goes to infinity goes to 0. And as s goes to infinity, 1 over square root of s also goes to 0. And this term, the exponent is going to 0. So that means that this whole term is going to 1, right? So this term goes to 0. This term, e to the minus square root of s, goes to 0. So as s goes to 0, f of s naught plus s goes to 0, right? And that's what we want to prove. So we'll stop there. Okay, so I'm not going to ask you to prove that on the exam, but if you wanted to know how that works out, and this is how mathematicians go about proving things, this is what you would do. You find ways of bounding some quantity you care about by other terms that end up still going to 0. And you have to use sort of these things like convexity, upper bound on the integrands, and etc. And then ultimately it gives you something like this, and if you chose everything right, it goes to 0. Choosing the square root of s, 1 over square root of s, as the endpoint here ends up being kind of critical, because we want basically this, this thing to go to 0 as s goes to infinity. If I just picked split it at, say, 1 instead of 1 over s, then we would end up, this end here would end up shrinking, but ultimately our bound would be like a triangle, and that wouldn't help us. So we needed something where the width was going to be decreasing, and that's why I picked this. And yeah, so that's what we got. And yeah, we'll cut back to my office or wherever we were when I recorded the end of this, because that was a week ago. Anyway, okay.
Okay, so all done. So that is the end of the solutions to differential equations using the Laplace transform. So next what we're going to do is we're going to skip to, I think it's 7.7. I'll have to double check. Maybe I'll put it ephemerally around me. And then what we're going to do is we're going to be talking about the convolution of two functions and Laplace transforms of convolutions. And this will allow us to solve yet another kind of what we call an integral equation. And this will lead to a lot of other interesting applications. Then after that, we'll see what we have time to do before the wrap up of the class. And yeah, it should be fun. All right, I'll see you next time. And I think I'm going to leave you with something else that's fun.